There's currently a great deal of research and development on metal organic frameworks for use as adsorbents in separations of a wide variety of mixtures that are important in the process industries. In the publications reporting these developments, it is commonplace to demonstrate the efficacy of the developed MOF for the specified separation application by conducting transient breakthrough experiments in small-scale equipment. As an example, I show here the experimental setup as used in this paper published in 2021 that reports the development of a new MOF, ZNU1, for separations of mixtures of C2H2 and CO2. The breakthrough experiments are conducted in a tube of internal diameter 4.6 millimeters diameter, and a length of the packed section is 100 millimeters. The flow rate of the gas mixture 50-50 for C2H2 and CO2 at the inlet is of the order of 2 milliliters per minute. This corresponds to a superficial gas velocity within the tube of about 5 millimeters per second. The experiments are invariably carried out under isothermal conditions. In sharp contrast to these laboratory experiments, industrial units are conducted at a significantly larger scale, as illustrated in this photograph here, and the column diameters are of the order of a meter or so. The column heights may be 7 to 10 meters. Instead of MOF crystals that are used in powder form in the laboratory, the MOF crystals are incorporated into binders that are used in the form of pellets, and the pellet diameter is typically 2 to 5 millimeters in size. It is not possible to use powdered MOF crystals within industrial units because the pressure drop experienced by the gas phase would be unacceptably high. The superficial gas velocities used within industrial fixed bed adsorbers is significantly higher than used in laboratory scale breakthrough apparatuses, and typically the gas velocity is of the order of 15 centimeters per second in place of 5 millimeters per second in laboratory experiments. The translation of the results obtained in small-scale laboratory equipment to commercial units is a topic for a future presentation. Today, I'm going to focus on the interpretation and presentation of transient breakthrough data obtained in laboratory scale equipment. In particular, I'm going to address the question of comparing the performance of various MOFs on the basis of breakthrough experiments. To start with, let us look at experimental data on transient breakthroughs for different MOFs for separations of mixtures of acetylene, C2H2, and CO2. Basically, there are two types of MOFs. MOFs which are selective to C2H2. Those are the three experiments shown here. and MOFs that are selective to CO2. Let's look at these experiments for the C2H2 selective MOFs. We note that the experimental data are presented in different forms. The y-axis is the same. They represent the concentrations of the gas mixture exiting the adsorber, normalized with respect to the concentration of that component in the inlet to the adsorber. But the x-axis is that is used in published data is in several different forms. The time could be represented in minutes, as in this case, for ZNU1, with a mass of adsorbent of 2.14 grams with an inlet flow rate of 5 milliliters per minute. In the same paper, the data for ZNU1 is presented in a different form, where the dimensionless concentrations of the two components at the exit to the tube are plotted against a parameter which is expressed as milliliters per gram. I'll return to this in my next slide. In this case, the data for a different MOF, ZU610, which is also a C2H2 selective MOF, the dimensionless concentrations of the two components at the exit are plotted against a parameter which has the units of minutes per gram, gram being the mass of the adsorbent. Let's turn to CO2 selective MOFs. Here we have data at two different temperatures for cerium Mil144F. These are data published by the group in NUS Singapore. This is a CO2 selective MOF with the advantage that the desired product C2H2 can be recovered in the adsorption cycle. But the data are plotted as the dimensionless concentrations on the y-axis against time in minutes. In this case, 0.55 grams of adsorbent are used, and the flow rate of the gas mixture at the inlet is 2 milliliters per minute. This is another CO2 selective MOF, ZU610A, where the dimensionless concentrations at the exit are plotted against a parameter with the units of minutes per gram, gram being the mass of adsorbent in the bed. However, the mass of adsorbent used is 0.85 grams in place of 0.55 grams here. So these two breakthroughs cannot be directly compared. And these three breakthroughs cannot also be compared in a straightforward manner. So we ask ourselves the question, how do we compare these breakthroughs to determine the ranking of the separation performance of the various MOFs? It is impossible to use this data as is to compare the breakthrough experiments, because the volumetric flow rates and mass of adsorbents used are not the same in each of these 5 different cases. So let's develop an understanding of how best to present experimental data and how to carry out the comparisons of the efficacy of different MOFs for a given separation task. Decide how best to present experimental data on transient breakthroughs, we need to understand a few important factors that determine separations. Firstly, separations improve with increasing contact time between the gas mixture and the MOF crystals within the packed tube. The contact time T is inversely proportional to the volumetric flow rate at the inlet to the tube. Separations also improve if increasing masses of adsorbents are packed into the tube, and therefore when presenting data on experimental breakthroughs and comparing experimental breakthroughs with different MOFs, with different masses of adsorbents and different inlet flow rates of the gas mixture, we need to use a normalized time axis. And the normalized time axis that is appropriate is shown here. It is the product of the actual time, T, say in seconds, multiplied by the volumetric flow rate of the gas mixture at the inlet, say in liters per second, divided by the mass of adsorbent in the bed, say typically in kilograms. So the x-axis has the units of liters per kilogram. To demonstrate that this is the appropriate x-axis to use, I present here experimental data for separations of 50-50 mixtures of C2H2 and CO2 using a MOF that is C2H2 selective. The data shown here were obtained with 5 different flow rates, 2 milliliters per minute, 5 milliliters per minute, and 10 milliliters per minute. But when used, when plotted against a normalized time axis, all the 3 sets of data collapse to uniform or unique curve. Therefore, this proves that the comparisons between MOFs could be made on the basis of a normalized time axis defined in this manner. Having established the appropriate way to plot experimental data on transient breakthroughs, let us use these data to evaluate MOFs. I show experiments for 199 mixtures of ethine and ethene obtained with 2 different MOFs, ZUL100 with shown by the red circles, and UTSA200 shown by the blue triangles. The objective is to produce purified ethene containing less than 40 ppm of C2H2. Visually, it is clear that purified ethene can be obtained during the time interval. Note that the x-axis is the normalized time axis. During the time interval indicated by the blue arrow, purified ethene can be obtained from UTSA200. A larger amount of purified ethene is possible with ZUL100. The productivities of purified ethene containing less than 40 ppm can be determined from the experimental breakthroughs using numerical integration. Further details on such calculations are provided in my paper published in ACS Omega in 2020. Here are experimental data for separations of 199 mixtures of propyne and propene. The objective is to produce purified propene containing less than 40 ppm of propyne. The data are for two different MOFs, NK MOF 11, shown by the black squares, and SIP6 2 copper interpenetrated, shown by the red circles. During the time interval indicated by the red arrow and black arrows, purified propene can be recovered. It is clear even from a cursory visual inspection that NK MOF 11 will result in a higher productivity of the desired propene. Further details are available in my paper. Here are experimental data for separation of 50-50 mixtures of CO2 and methane at a total pressure of 100 kilopascals. The data are obtained with 4 different MOFs, with the gray colored symbols are for Cureha carbon. The red circles are for nickel MOF 74, or the cyan colored symbols are for MIL 53, and the green colored symbols are for ammonium MIL 53. During the time interval indicated by the red arrow, black arrows, green arrows, and cyan arrows, it is possible to recover purified methane, and the numerical integrations can be performed to determine the precise productivities of the purified product, say typically containing less than 1% CO2. Details are available in my paper. The message here is that if the desired product can be recovered in the adsorption phase of a PSA process, then evaluation of MOFs using experimental breakthroughs is rather straightforward, because the data with different MOFs can be compared purely on the basis of experimental breakthroughs. Let's proceed to examine a slightly more complex situation. Let us evaluate MOFs for separations of mixtures of C2H2 and CO2. There are two classes of MOFs: a set of MOFs that are selective to CO2, and the important advantage of such MOFs is that the desired product, that is C2H2, can be recovered in purified form in the adsorption phase of the PSA process. Here I present data for two different MOFs, ZU610A, shown with green squares, and cerium MIL 144F, shown with the red lines. Purified C2H2 can be recovered during the time intervals indicated by the green arrow and the red arrow. A visual inspection of the experimental breakthroughs with these two MOFs seems to indicate that the productivities of pure C2H2 obtained with these two different MOFs is very small and nothing to write home about. more detailed calculations using numerical integrations will be required to calculate the productivities of 99% pure C2H2 and can be compared. Now the situation is significantly more complex for evaluating C2H2 selective MOFs. Most of the MOFs that have been presented in the published literature are selective to C2H2. In this case, C2H2 can only be recovered in purified form in the desorption cycle. However, most of the experimental data that are available have been published only for the adsorption cycle, where only thing that has been demonstrated is the separation capability of the MOF. I show here a set of two experiments with FJU90 shown by the open symbols and ZNU1 shown by the filled symbols. It is clear from these breakthrough experiments for the adsorption cycle that ZNU1 has a significantly higher uptake by about a factor 2 higher than that for FJU90. But concomitantly, significant amounts of C2H2 are absorbed by both MOFs. The only way to compare the MOFs appropriately to determine the productivity of 99% pure C2H2 is to compare experimental data for the desorption cycle. Now, such experiments are rather rare. In the paper cited here, desorption experiments have been presented for ZNU1, and the data for ZNU1 are compared with the data for other MOFs by simulations of the desorption cycle. Simulations. And for further details, I refer you to the Angaman Shemi paper in 2021, where the desorption simulations are described and used for comparing the productivities and purities of the different MOFs for C2H2 CO2 separations. All these MOFs that are compared are C2H2 selective. I also discussed this in my presentation evaluating MOFs for C2H2 CO2 mixture separations on my YouTube channel. So the message is, if the MOF is CO2 selective, comparing MOFs using experimental breakthroughs is rather straightforward. However, if the MOFs are C2H2 selective, then comparing MOFs based on desorption experiments is rather more complicated for two separate reasons. Firstly, very few desorption experiments have been reported so far, the only exception being this paper, as far as I'm aware. But also, in the laboratory scale, these desorption of the desired products is almost invariably carried out using an inert gas. Such a desorption strategy is never applied in industrial practice. In industrial practice, the desorption would be by, say, vacuum desorption, or just reducing the pressure or changing the temperature. But in experimental breakthroughs, it is more convenient to use isothermal conditions and use desorption using an inert gas. And it would be rare to find experimental data for the desorption cycle in which the desorption experiments are carried out in the same manner, unless these experiments are conducted by the same experimental group, research group. I'll leave it at that, leaving with the takeaway message that we need to use desorption simulations in order to compare the MOFs in a correct manner. We move on to a comparison of MOFs for separations of mixtures of propene and propane. In industrial practice, the objective would be to produce purified propene with a purity of 99.95% that is suitable for use as a feedstock to the polymerization reactor. However, most of the MOFs, indeed almost all MOFs that have been reported in the literature, are selective to propene, and therefore purified propene can only be recovered in purified form in the desorption cycle. But let's look at the adsorption cycle to gain some insights into the likely performance of different MOFs for the separation. I here present experimental data. Just these are copied from the papers. The background information to these publications is available in my paper. We have cobalt gallate that selectively excludes propane, or virtually excludes propane, because of subtle differences in the sizes and shapes of the alkene and alkane. Here we have experimental data for Kaust-7 shown with the black lines. This excludes propane due to subtle trapdoor effects and making use of differences in the bond lengths and bond angles between C3H6 and C3H8. Then we have data here for zeolite 4A, and the red lines and orange lines are for zeolite 5A. Here we have experimental data for the adsorption cycle and desorption cycle for iron MOF 74 that were published in the science paper of Jeffrey Long and co-workers in 2012. This is an oft-cited paper. Then even a visual inspection will indicate that there are important differences in the breakthrough characteristics of cobalt gallate, Kaust-7, and iron MOF 74. Important difference is that for iron MOF 74, the uptakes of both components are significantly high, and for cobalt gallate, due to size exclusion, almost no propane is absorbed into the pores. The same is true for Kaust-7. We also note that the breakthrough data are presented in quite different forms. Here the outlet concentration is presented as a function of time. Here the dimensionless concentrations at the exit are presented as a function of the actual time. Here the compositions at the outlet are expressed as a function of the breakthrough time. The temperatures are also not exactly the same. Here it's 298 in these experiments. However, for iron MOF 74, the experiments were reported at a temperature of 313 Kelvin. The masses of adsorbents used in these three sets of papers is also different, and the flow rates are also different. The first thing to do is to make a comparison of the absorption cycle of C3H6, C3H8 separations for data sets that are obtained under the same conditions and using a normalized time axis. Let's do that in the next slide. In this graph, I compare the experimental data for 4 different MOFs: Kaust 7, cobalt gallate, LTA5A zeolite, and nickel MOF 74 for 50-50 mixtures of propene and propane at a temperature of 298 Kelvin and total pressure of 100 kilopascals. The comparisons are made on the basis of the normalized time parameter Q naught, the flow rate at the inlet times the breakthrough time divided by the mass of adsorbent in the bed. The objective, to repeat myself, is to produce purified propene, but that can be only done in the desorption cycle. But we gain some insights by examining the breakthroughs of the adsorption cycle. The most important differences are between Kaust 7 and cobalt gallate on one side and nickel MOF 74 on the other side. For these two MOFs, Kaust 7 and cobalt gallate, almost no propane is adsorbed within the pores, whereas with nickel MOF 74, a significant uptake of propane occurs. Now, during the desorption cycle, any propane that is remaining within the void pores will reduce and influence the purity of the desired propene product in the desorption cycle. So generally speaking, it is preferable to have an adsorbent that rejects propane completely into the gas phase so that the higher purities can be attained in the desorption cycle. Indeed, we need to compare these MOFs by performing simulations of the desorption phase, and such simulations are relatively simple to carry out, and they are presented in my YouTube presentation, Polymer Grade Propene Feedstock with MOFs, ? And this presentation leads to the conclusion that higher purities are achievable with cobalt gallate and Kaust 7, but the productivities of purified C3H6 are rather low. Here we have with nickel MOF 74 severe restrictions on the purities that are achievable unless you adopt a rather complicated five-step PSA scheme. Even so, it appears that it is near on impossible to produce 99.95% pure C3H6 using nickel MOF 74. Further research is required for developing MOFs for this separation that are aimed at rejection of propane almost totally from the pores. I will leave this discussion at this point.